This course is an introduction to mobile hydraulic systems. You'll learn how these systems work and why they're used on Caterpillar machines. Completion of this course will prepare you for Level 3 courses on hydraulic systems for specific Caterpillar machines. This chapter on basic hydraulic concepts contains information you need to know to effectively discuss or repair Caterpillar hydraulic components or systems. It's important to review these system and safety fundamentals since they provide the foundation upon which the rest of this course is built. This lesson examines the role of hydraulics in Caterpillar construction and material handling equipment. The power to lift, to push, the power to move mountains or build them. In the world of construction and material handling equipment, the power that gets the job done is hydraulics. It was not until the 1950s that hydraulics were widely used on Caterpillar equipment. Since then, this form of power has become essential to the operation of virtually every machine in the Caterpillar line. Cylinders of every type and size give life to buckets, blades, backhoes, and truck beds. Hydraulic motors drive tracks, wheels, car bodies, and conveyors. Brakes, steering, transmissions, suspensions, and a host of other vehicle systems rely on hydraulics for power and control. This course is an introduction to mobile hydraulic systems. You will learn how these systems work and why they are used on Caterpillar machines. Salespeople taking this course will focus on the features and benefits of Caterpillar systems. You will be better prepared to talk knowledgeably with your customers about the advantages of Caterpillar hydraulics. Service people will explore the function, wear, and failure of hydraulic systems and the options for repairing them. The course will prepare you for Level 3 courses on hydraulic systems for specific Caterpillar machines. In this chapter, you'll learn the names and functions of components in simple hydraulic circuits and how hydraulic energy is put to work. This chapter also includes a segment on safety. The Components chapter is an in-depth study of hydraulic components used on Caterpillar machines. It explains the different types of pumps, motors, valves, and other components, how they work, wear, and fail, their repair options, and significant sales features. Upon completing this topic, you'll be able to identify fundamental hydraulic system components, define basic hydraulic terms, and discuss the properties of hydraulic fluids. Objective: given a basic diagram of a mobile hydraulic system, you'll be able to identify and use the correct names for system components. In this lesson, you'll learn about basic hydraulic components and how the system operates. This diagram represents a basic hydraulic system. Note that the hydraulic lines are different colors. The red, blue, and green represent different pressures within the system. Common system components include A. Fluid, B. Tank, C. Filter, D. Pump, E. Control valve, F. Actuator, G. Lines, H. Relief valve, I. Cooler. The fluid in a hydraulic system transmits energy. This is possible because liquids are virtually incompressible. As fluid is pumped through the system, force is exerted equally on all surfaces. Since liquids conform to any shape, the hydraulic fluid can flow in any direction and into all open passages. Oil is the most commonly used hydraulic system fluid in Caterpillar machines. The primary functions of a hydraulic tank are: stores oil, cools oil, allows air to separate from oil, allows particles to settle. Filters remove contaminants from the hydraulic fluid. This prevents component damage and ensures proper system operation. The location and type of filters in a system vary. The pump converts mechanical energy into fluid energy in the form of flow. It's driven by an external power source. The directional control valve determines the path fluid takes through the system. This is the means by which the operator controls the machine. The actuator converts hydraulic energy to mechanical energy in order to perform work. Cylinders produce linear motion, used to operate buckets, blades, booms, and other implements. Hydraulic motors produce rotary motion, used for motive, steering, and other vehicle systems. Lines are hoses or tubes through which hydraulic fluid moves. Flexible hoses allow for motion, absorb vibration, reduce noise, and are easy to route and connect. Tubes provide more rigid connections, compact routing, and better heat dissipation. The relief valve, or pressure control valve, limits system pressure. The valve opens if pressure exceeds a predetermined set point. A cooler removes heat from the hydraulic fluid. This improves component life. This animation will help demonstrate how the system operates. The control valve is now in the raise position. Follow the arrows as they trace flow through the system. Note how the system operates differently when the control valve is in the lower position. Objective. Given a basic diagram of a mobile hydraulic system, you'll be able to identify both series and parallel circuits. This diagram represents a simple hydraulic system with one valve and one actuator. Most machines require multiple components which can be connected in series or parallel. This lesson examines the difference between these two types of circuits. When components are connected in series, fluid flows from one component to the next. There is one path for flow, as shown in illustration number 1. When components are connected in parallel, fluid flows through each component simultaneously. There are 2 or more paths for flow, as in illustration 2. In a series circuit, fluid flows from one component and through one or more additional components before returning to the tank. In this circuit, valve B gets pump flow before valve A. In a parallel circuit, components have equal access to pump flow. In this circuit, valves A and B receive flow simultaneously, permitting independent operation. Objective. Using commonly available service literature, you'll be able to locate and identify hydraulic system components in Caterpillar machines, particularly those systems in track loaders, backhoe loaders, and excavators. The track loader is representative of machines with simple hydraulic systems. Here you can identify each of the major components. 1 is the cooler, 2 the pump, 3 the lift cylinders, 4 the hydraulic tank, 5 the tilt cylinder, and 6 the control valves. The cooler removes excess heat from hydraulic return oil before it flows to the tank. Air from the engine fan carries the heat away. The pump draws oil from the tank and supplies it to the control valves. The lift cylinders receive oil from the lift control valve to raise and lower the bucket. The hydraulic tank serves as a reservoir of supply oil to the system. This tank contains 2 oil filters which clean the oil before it is combined with reserve oil. The tilt cylinder receives oil from the tilt control valve to rack back and dump the bucket. The control valves provide the operator control of lift and tilt cylinders by directing oil to the appropriate cylinder ports. Oil flows from the cylinders through the valves and cooler, then returns to the tank. The backhoe loader is a small machine, but it features a complex, sophisticated hydraulic system. This diagram identifies the major components. 1. Backhoe cylinders. 2. Stabilizer cylinders. 3. Swing cylinders. 4. Steering cylinder. 5. Pump. 6. Tilt cylinder. 7. Lift cylinders. 8. Hydraulic tank. 9. Control valves. The backhoe cylinders include the boom, stick, and bucket cylinders, which control the operation of the backhoe. Stabilizer cylinders extend to the ground to steady the machine during backhoe operation. Swing cylinders move the backhoe from left to right. The steering cylinder pivots the machine's front wheels left and right. The pump draws oil from the tank and supplies it to the control valves. The tilt cylinder racks back and dumps the bucket. The lift cylinders raise and lower the bucket. The hydraulic tank serves as a reservoir of supply oil to the system. Housed inside the tank are 2 oil filters which clean the oil before it's combined with reserve oil. The control valves direct oil to various cylinders. Caterpillar hydraulic excavators depend on powerful, efficient hydraulic systems to do their jobs. As you can see from this diagram, the system has several major components. This diagram identifies the location of 1. Control valves, 2. Track motors, 3. Pumps, 4. Hydraulic tank, 5. Boom cylinders, 6. Stick cylinder, and 7. The bucket cylinder. Control valves direct oil to the cylinders and track motors. The track motors provide rotary power to drive the tracks. The pumps draw oil from the tank and supply it to the control valves. The hydraulic tank serves as a reservoir of supply oil to the system. The filter, located inside the tank, removes contaminants from the oil, which is returning to the tank. The 2 boom cylinders raise and lower the boom. The stick cylinder extends and retracts the stick. The bucket cylinder opens and closes the bucket. Objective: you'll be able to discuss the properties of hydraulic fluid. Hydraulic fluid is the key component in any hydraulic system. It's the means by which energy is transmitted throughout the system. Certain fluid properties determine how well it does its job. This lesson discusses critical properties and fluid additives used to improve them. Hydraulic fluid has many functions. The fluid must transmit energy throughout the system, provide lubrication for moving parts, protect components from rust and corrosion, carry heat away from components. One of the most critical properties of oil is viscosity. This refers to an oil's thickness or its resistance to flow. Viscosity is directly related to how well an oil will protect and lubricate components. High viscosity oil can result in sluggish operation and may require additional power. Low viscosity may decrease the fluid's ability to lubricate and cause components to wear faster. It also increases the possibility of leakage. Temperature can affect the viscosity of oil, so it's important to use the proper weight of oil for your machine and climate. Always refer to your operators and maintenance guides for the recommended oil. Additives are used to control viscosity and other important characteristics of hydraulic oil. They're used to reduce wear, increase chemical stability, inhibit corrosion and oxidation, keep components clean, and suspend particles until they reach the filter. These are additional reasons why you should always use the recommended hydraulic fluid in Caterpillar machines. Upon completing this topic, you'll be able to solve mathematical equations relating to force, pressure, and area, and you'll be able to convert hydraulic-related units of measure from English to metric and vice versa. Objective: you'll be able to trace the conversion of power in a mobile hydraulic system. In order to perform useful work, a hydraulic system must convert and control energy as it flows from one component to the next. This graphic represents the key conversion and control points in the system. A hydraulic system must receive input energy from some source. This is usually in the form of rotating mechanical energy from an engine or vehicle gear train. The hydraulic pump converts mechanical energy to hydraulic energy in the form of flow. Valves control the transfer of hydraulic energy through the system by controlling fluid flow and direction. The actuator converts hydraulic energy to mechanical energy in the form of linear or rotary motion and force. This energy is used to perform work. Objective: using a calculator and data from the service manual, you'll be able to calculate optimum hydraulic system performance. The cycle time of an actuator is a function of its 1. Displacement or volume, and 2. Flow rate or quantity of fluid moved in a given time. Given the same flow rate, an actuator with a larger displacement will have a slower cycle time than one with a smaller displacement. Increasing the flow rate increases the speed of the actuator. Let's begin by calculating the displacement of this cylinder. Displacement equals piston area, number 1 on the graphic, times piston travel, the distance indicated by number 2. In this case, displacement equals 5.00 inches squared times 20.00 inches. Thus, displacement is equal to 100.00 inches cubed. The metric equivalent of this calculation would be displacement equals 32.3 centimeters squared times 50.8 centimeters. Displacement equals 1,640.8 centimeters cubed. Knowing actuator displacement, indicated on the graphic as number 1, and the rate of flow entering the actuator, number 2, we can calculate its cycle time. Cycle time equals displacement divided by flow rate. Cycle time equals 100.00 inches cubed divided by 460.00 inches cubed per minute times 60 seconds per minute. Or in metric equivalent, cycle time equals 1,640.8 centimeters cubed divided by 7,538 centimeters cubed per minute times 60 seconds per minute. The cycle time equals 13.1 seconds. In this example, it will take the piston 13.1 seconds to travel its full length. The relationship between flow rates and displacement can be a useful troubleshooting tool. The correct cycle times for a machine are often listed in the service manual. If these values differ from measured times, the flow rate into the cylinder is not what it should be. This is the first step in identifying the cause of erratic or sluggish performance. So far, we've talked about fluid flow in a hydraulic system. If this flow is restricted in any way, such as placing a load on a cylinder, pressure is created. The amount of pressure can be calculated by dividing the force of the load by the area over which it's applied. This is an application of Pascal's law. The textbook definition of Pascal's law is, a force applied to a confined liquid is transmitted equally in all directions. This can be expressed using these 3 formulas. Pressure equals force divided by area, force equals pressure times area, or area equals force divided by pressure. Said another way, pressure can be defined as a specific force acting on a specific area. This symbol is often used as a means of remembering the equations. It's used by covering the variable you want to calculate. The expression that remains is the equation. For example, to calculate pressure, cover the P, and the remaining expression is F divided by A. Effective piston area is the area upon which hydraulic pressure acts. If an equal pressure is applied to both ends of a piston, a greater force is exerted on the head end of the piston. This is because the rod must occupy part of the piston area, reducing effective area on the piston rod end. In summary, Pascal's law can be used to describe the relationship between pressure, force, and area. It's expressed by the formula P equals F divided by A. Applying this formula to pistons, the amount of pressure required to lift a load is equal to the resisting force of the load divided by the effective area of the piston. Objective: using a calculator and proper conversion tables, you'll be able to convert metric hydraulic measurement into English units or English into metric. Many different English and metric units of measurement can be used to express pressure, force, area, and flow. It may be necessary from time to time to convert one unit of measurement to another. This table shows common English to metric conversion factors. This table shows common metric to English conversion factors. For example, you've drained the oil from a hydraulic tank and are preparing to refill it. The service manual says it holds 36 liters. You need to convert this to gallons for your maintenance report. To make the conversion, you need only find the appropriate conversion factor from a table such as this and multiply it by the unit you wish to convert. 36 liters times 0.264 equals 9.5 gallons. There are other conversions that you should be aware of. For example, the terms in this table are all used to express pressure. Upon completing this topic, you'll be able to list proper safety procedures to follow when working on a mobile hydraulic system, and you'll be able to identify potential safety hazards. Objective: you'll be able to identify proper work and safety procedures that should be followed when servicing hydraulic systems. In this topic, we discuss general safety procedures that should be observed while working on or around mobile hydraulic systems. Caterpillar hydraulic systems are designed for safe, trouble-free operation. Even so, it is wise to remember that these systems are built for rough, demanding work. This means high pressures, hot oil, and heavy loads. There are some general safety procedures that should be performed before working on any mobile hydraulic system. 1. Shut down and tag the machine. 2. Block or lower implements and block wheels or tracks. 3. Relieve pressure in the hydraulic system. 4. Restore the system for operation following repairs. Following are examples of each process. There are a few general machine shutdown procedures that should be followed when preparing to service the hydraulic system. If you are in the field, move the machine to level ground, away from working machines and people. Activate the parking brake, then lower or block the implements and stabilizers. Stop the engine and engage the transmission lock. Then tag the machine to let others know the machine is being serviced. Be sure you do not forget this critical step. The preferred place to place the tag is on the steering wheel or steering levers. Check the operation and maintenance guide and service manual for any special shutdown procedures, and you are ready to begin service operations. Blocking procedures will vary from machine to machine and depend on the particular components that require service. A general rule of thumb is to always block the wheels or tracks to prevent both forward and rearward movement. Implements should always be blocked with wooden blocks, never concrete. Make sure the blocking is sufficient to carry the load and that it is securely positioned. Some machines are equipped with special blocking equipment. For example, some wheel loaders require blocking of the articulation joint. A special bracket is provided for this purpose. Backhoe loaders and other machines are equipped with special brackets to hold the loader frame for certain service tasks. Always remember to check the operation and maintenance guide and service manual for any special blocking procedures. System pressure must always be relieved before servicing the hydraulic system. Hydraulic oil can become a deadly projectile if a pressurized line is broken. After lowering or blocking implements and shutting down the engine, all hydraulic control levers should be moved through all possible positions. This ensures that pressure is relieved in cylinders and lines. Loosen the hydraulic tank filler cap and bleed the accumulator if the machine system you are servicing is equipped with one. Brake and steering system accumulators can be bled by pumping the brake pedal or turning the steering wheel a few times. After service or repairs are completed, remember to add additional hydraulic oil if necessary. Replace the tank filler cap, remove the tag, and operate the machine to make sure the system is in proper working order.
It is your responsibility to be familiar with and heed all warning labels and placard information on the equipment. And remember, always refer to the appropriate service manual of operation and maintenance guide and any other disassembly and assembly manuals for a machine before working on the hydraulic system.